Hi, it's Sir Rob. Today I am going to talk about another operations research optimization tool, the logistics transportation optimization method. This method is developed to optimize solutions to logistics, transportation, or distribution problems. It is a specialized and foundational class of linear programming optimization method within the field of operations research. As always, in the practice of accountancy, we should remember to be professional, perform effectively and efficiently, follow standards, and document our work adequately and properly. Topics in this lecture video include 1. The nature of logistics, transportation optimization method. 2. Application of logistics, transportation optimization method. 3. Components of, or the common terminologies used in transportation problems. 4. Types of logistics, transportation problem, and 5. Solving transportation problems using MS Excel Solver. And off to our first topic. What is logistics, transportation, optimization? Logistics, transportation optimization is a specialized and foundational class of linear programming problems within the field of operations research, developed as a structured and elegant approach to the optimal allocation of resources from multiple origins to various destinations at a minimum total cost. Problems related to logistics, transportation optimization arise in planning for the distribution of goods and services from several supply locations to several demand locations, which creates for an organization the need to determine the most efficient way to move goods or services from multiple supply points to multiple demand points. These problems are common in business and industry because most companies operate with several production facilities, warehouses, or distribution centers that must supply products to a network of stores, customers, or service areas. The challenge lies in deciding how much to ship from each supply location to each demand location so that all requirements are met without exceeding available supply, all while minimizing total transportation costs, travel times, or other relevant measures. Such problems are not limited to physical goods. They can also involve the allocation of services, resources, or personnel to various locations where they are needed. For example, hospitals might allocate medical supplies to different clinics, or a company might assign delivery trucks to customer zones. This method is a critical tool in logistics, supply chain management, and industrial planning. Its primary objective is to find a cost-effective shipping schedule that satisfies both supply and demand constraints, thereby reducing transportation expenditures and improving overall operational efficiency. The transportation model's enduring importance is underscored by its ability to simplify complex real-world systems into a manageable, numerical framework that can be solved systematically. Application of logistics, transportation optimization. Logistics, transportation optimization have wide-ranging applications across many industries because efficient distribution is critical to business success. One of the most common applications is in the distribution of goods from factories to warehouses or retail outlets. Companies must decide how to allocate shipments from multiple production plants to various regional warehouses or directly to stores in a way that minimizes overall shipping cost while meeting customer demand. Another important application is the assignment of tasks, jobs, or resources, which is actually a special case of the transportation problem. For example, assigning workers to projects, machines to jobs, or vehicles to routes can be formulated and solved using transportation models to maximize efficiency. However, these entail non-financial decisions and therefore, we will not cover as students of the accountancy program. Transportation optimization plays a vital role in scheduling shipments, which is one of the most critical aspects of supply chain management. It is not enough to simply decide where goods should be sent. Organizations must also determine when and how much to ship in order to meet customer demand on time and avoid shortages or overstocking. By using optimization models, businesses can create shipment schedules that align production output with demand patterns, reduce storage costs, and minimize transportation expenses. For instance, a company can plan the most efficient delivery timetable so that goods leave the warehouse just in time to replenish store shelves, eliminating unnecessary holding costs. Effective shipment scheduling also helps organizations deal with capacity constraints, such as limited truck availability, loading dock times, or restricted shipping routes. It can balance workloads across different carriers or transport modes, ensuring no single route is overused while others are left idle. This level of coordination is especially important in industries with perishable goods, where late deliveries could lead to waste and financial loss. In summary, transportation optimization ensures that the right quantity of goods reaches the right destination at the right time, making the entire supply chain more reliable, cost-effective, and responsive to changes in demand. Beyond business, transportation models are applied to network logistics and humanitarian operations, such as optimizing routes for disaster relief supplies to reach affected areas quickly and at minimal cost. In modern supply chain and logistics management, transportation models support strategic decision-making, helping organizations reduce costs, balance workloads, and improve service levels. Whether in manufacturing, retail, shipping, public service, or even digital services allocation, logistics optimization serves as a fundamental tool for achieving efficient and cost-effective distribution.
Components of logistics transportation problems. 1. Sources. The first essential component of the transportation problem is the sources, also called supply nodes. These represent the origins of goods or resources, such as factories, warehouses, or production plants, that are responsible for fulfilling customer needs. Each source is characterized by its supply capacity, which indicates the maximum quantity of goods it can provide for distribution. In the mathematical model, each source has a supply constraint, ensuring that the sum of shipments leaving the source does not exceed its available supply. 2. Destinations. The second key component is the destinations, also called demand nodes. These are the points where goods must be delivered, such as retail stores, regional depots, or customer locations. Each destination is associated with a specific demand requirement, which must be satisfied in order to meet customer needs or market obligations. In the mathematical model, each destination has a demand constraint, which ensures that the total goods received from all sources meet or exceed its demand level. 3. Routes. The third component consists of the routes that connect each source to each destination. Each route has an associated transportation cost per unit, which represents the expense of shipping goods along that path. Routes can also have capacity limits if only a certain number of goods can be shipped through them due to physical, contractual, or logistical constraints. These costs are organized in a cost matrix or represented as arcs in a network diagram, and they play a crucial role in determining the optimal shipping plan since they directly affect the total cost of transportation, as we shall see later when we will be solving some problems. In some types of logistics or transportation problems, the cost of transportation is replaced by other constants like sales, profit, number of days to deliver, or some other entities that management would use to find the optimal solution to a specific problem. However, in our classroom discussion, we will limit our problems to costs. 4. Network nodes and arcs diagram view. The network is a graphical representation of the entire transportation problem, showing all sources, destinations, and the possible routes connecting them. It is made up of nodes, or points, and arcs or lines. The nodes represent the supply points, or sources, and demand points, or destinations, while the arcs represent the routes along which goods can be shipped. Each arc is usually labeled with the cost per unit of transportation and sometimes its capacity limit. In other words, a network visually maps the flow of goods from multiple origins to multiple destinations, making it easier to understand relationships, constraints, and potential optimization opportunities in the problem. 5. Decision variables, not seen in diagram. The decision variables represent the quantities to be shipped along each available route, typically denoted as X subscript ij, where I refers to a source and J refers to a destination. These variables are the unknowns that need to be determined in order to minimize total cost while satisfying all supply and demand constraints. They must be non-negative and may be required to be integers in some cases, such as when dealing with indivisible shipment units like trucks or containers. 6. Objective function, not seen in diagram. Finally, the objective function. The goal of solving the transportation problem is to determine exactly how much of the product should be shipped from each source to each destination in a way that achieves the most cost-effective distribution plan. This means identifying the values of all decision variables, the quantities to be transported along each available route, so that the total transportation cost is minimized while still meeting every destination's demand, and not exceeding any source's supply. In practice, this involves balancing supply and demand across the network, selecting which routes to use, and determining how much to send along each one. The solution is considered optimal when it satisfies all the problem's constraints and no other possible distribution pattern would lead to a lower overall cost. Essentially, it provides managers with a clear, data-driven shipping plan that uses resources efficiently, avoids waste, and ensures customer needs are fully met at the lowest possible expense. Types of logistics transportation problems. Transportation problems can be classified into several types depending on the relationship between total supply and total demand, as well as the objective of the problem. The most common type is the balanced transportation problem, where the total quantity available at all sources is exactly equal to the total quantity required at all destinations, because supply and demand are perfectly matched. The solution simply redistributes available goods without leaving any surplus or shortage. This type of problem is often easier to solve mathematically, since no dummy sources or destinations are needed. When the total supply does not equal the total demand, we have an unbalanced logistics transportation problem. If total supply is greater than total demand, there is an excess quantity that cannot be delivered to any destination. To solve this problem, a dummy destination is introduced with demand equal to the excess supply. The cost of shipping to this dummy destination is typically set to zero as no actual transportation occurs. However, in some cases, the cost may represent a holding or storage cost for the excess inventory at the source. The decision to use a non-zero cost represents a strategic business choice about how to manage overproduction. Conversely, if total demand is greater than total supply, a dummy source is introduced with supply equal to the unmet demand. Again, its costs are set to zero, effectively representing backorders or shortages, so that the mathematical model remains solvable. The cost from this dummy source can, more commonly, be set to a high penalty cost to reflect the expense associated with unmet demand, such as lost sales or the cost of sourcing from an emergency supplier. This forces the model to minimize the costly unmet demand, providing a solution that quantifies the most efficient way to manage a supply shortfall. The use of dummy variables is a powerful example of how the mathematical model can be adapted to represent and inform critical business decisions. It transforms a pure optimization problem into a strategic planning tool that explicitly accounts for the trade-offs of holding inventory or experiencing stockouts. Another important type is the maximization transportation problem, which seeks to maximize sales, profit, or other benefits rather than minimize cost. In this case, the sales or profit per unit shipped is entered into the model, and the objective function is changed from minimizing total cost to maximizing total profit. This type of problem is common in revenue allocation or resource assignment scenarios where managers want to achieve the best possible outcome in terms of gains rather than cost savings. Finally, there are variations and special cases such as capacitated transportation problems where routes have upper shipment limits, time-constrained problems where shipping times must be minimized or deadlines met, and multi-objective problems where both cost and service level are considered. These variations reflect real-world complexities and often require more advanced solution methods than the Excel solver.
Solving logistics transportation problems using Excel Solver. The Microsoft Excel Solver add-in is a powerful tool for finding optimal solutions to a variety of constrained optimization problems. When tasked with solving a logistics transportation problem, the Excel Solver employs the Simplex LP linear programming solving method. This method is the appropriate choice because transportation problems are a classic and well-defined subclass of linear programming problems. The objective function, which seeks to minimize the total cost of shipments, is linear, as are all the constraints related to supply at sources and demand at destinations. The simplex LP solving method is based on the simplex algorithm, a foundational and highly robust computational procedure for linear optimization. Developed by Frontline Systems, the creators of the Excel solver, this method is designed to efficiently find a globally optimal solution for any linear model, provided one exists. For the majority of business applications, the standard Excel solver's implementation of the simplex LP method is more than sufficient. Its robustness and reliability have been proven over decades of use. However, for those working with exceptionally large-scale models with thousands or even millions of decision variables, the general-purpose nature of the standard solver may lead to performance limitations. In such cases, the use of dedicated commercial solver engines from developers like Frontline Systems is recommended, as they employ more powerful and specialized algorithms, such as the network simplex method, that are designed to handle the scale and unique structure of these complex problems with greater efficiency. Guide to solving using Excel solver. A. Formulating the spreadsheet model. The first step in solving a transportation problem is to correctly formulate the model in an Excel spreadsheet. This requires setting up three main sections. 1. Unit costs. A table or range of cells containing the cost to ship one unit from each source to each destination. 2. Supply and demand. A column for the available supply at each source and a row for the required demand at each destination. 3. Shipment variables. A blank table where the solver will place the number of units to be shipped along each route. These are the changing variable cells. B. Configuring the solver parameters. With the spreadsheet model formulated, the next step is to configure the solver parameters. Access Solver. On the Data tab in the Analyze group, click the Solver button. 1. Set Objective. In the Set Objective box, point your mouse to the cell reference where the formula for minimized total cost is entered. 2. Optimize for minimum. Click the Min radio button to indicate that the goal is to minimize the total cost. 3. Set Changing Variables. In the By Changing Variable Cells box, click and drag the mouse over the range of cells corresponding to the decision variables, which is the blank shipments table. 4. Add Constraints. Click Add to enter the constraints. For the demand constraints, select the row of Demand Destination Constraint Amount, the operator to greater than or equal to, and then select the row of Limit. For the supply constraints, select the column of Supply Constraint Amount, the operator to less than or equal to, and then select the column of Limit. 5. Check the box for Make Unconstrained Variables Non-Negative. 6. Select Solving Method. From the Select a Solving Method drop-down menu, choose Simplex LP. This is the critical step that directs the solver to use the correct algorithm for this linear problem. Solve, click the Solve button. The solver will perform its calculations and provide a solution. Presented here is the accomplished solver parameters for our sample problem. C. Interpreting the optimal solution. After the solver has completed its calculations, a dialog box will appear. If a solution was found, the shipments table will be populated with the optimal number of units to ship along each route to achieve the minimum total cost. It is important to review the Solver Results dialog box to ensure that a feasible and optimal solution was found and that all constraints have been satisfied. If a big question or exclamation mark in red font appears, it means that there is a problem with either your solver parameters or the formula in your spreadsheet model. Presented here is a Solver Solution dialog box which indicates that the optimal solution to the problem is found. There it is. Chapter 4, OR Optimization. Logistics Transportation Optimization Method. In summary, logistics transportation optimization is an essential, multi-dimensional discipline dedicated to the efficient allocation and movement of resources from sources to destinations. It is a cornerstone of operations research that provides a robust and elegant framework for optimizing resource allocation. It serves as a powerful conceptual foundation for understanding and modeling fundamental trade-offs in supply chain management. By forcing the explicit consideration of costs associated with storage, stockouts, and delivery routes, the model helps managers make more informed and strategic decisions. Ultimately, this optimization method remains an indispensable tool for minimizing costs, maximizing efficiency, and providing a foundational understanding for a wide array of more advanced optimization challenges in a dynamic and interconnected world. Logistics transportation optimization is a powerful tool in supply chain management because it ensures that the right quantity of goods is delivered to the right destination at the right time. This principle, often called the 3 rights of logistics, is critical for maintaining smooth operations and customer satisfaction. By carefully planning shipment routes, schedules, and quantities, transportation optimization reduces the likelihood of stockouts, delays, or costly overstock situations. It aligns the flow of goods with actual demand, so resources are not wasted on unnecessary shipments, and customers receive products exactly when and where they are needed. Beyond cost savings, this optimization makes the supply chain more reliable and predictable, which builds trust among suppliers, distributors, and customers. It also enhances cost effectiveness by minimizing fuel consumption, reducing warehouse holding costs, and preventing inefficiencies like half-empty trucks or redundant trips. Perhaps most importantly, transportation optimization makes the supply chain more responsive to demand fluctuations. For the majority of business applications, the standard Excel solver's implementation of the Simplex LP method is more than sufficient. Its robustness and reliability have been proven over decades of use. However, for those working with exceptionally large-scale models with thousands or even millions of decision variables, the general-purpose nature of the standard solver may lead to performance limitations. In such cases, the use of dedicated commercial solver engines from developers like Frontline Systems is recommended, as they employ more powerful and specialized algorithms, such as the Network Simplex method, that are designed to handle the scale and unique structure of these complex problems with greater efficiency. Listed on the slide are the references used in the production of this lecture video. Thank you and stay safe always.